Welcome to this explainer. Today, we're doing something I am absolutely super excited about. We're going to literally tear down a computer, right down to its absolute core components. If you've ever wondered what exactly happens behind the scenes, from the very fraction of a second you click a mouse to the moment an image pops up on your screen, you are exactly in the right place. We are going to chart the complete, fascinating journey of data. Okay, let's dive into this. Here is our roadmap to demystify how these machines actually process data. We'll hit the IPO cycle, peek inside the computer's brain, explore the memory hierarchy, and wrap up with the software that makes the whole shebang run. Kicking things off with Section 1, the IPO cycle. You know, every single computing device out there, from a tiny calculator to a massive supercomputer, follows one fundamental, unbreakable rule of data movement. And here it is, the ultimate blueprint. This brilliantly illustrates the entire complete journey. Data enters through the input unit, shoots straight into the central processing unit, where it mingles with the arithmetic logic unit and the control unit, parks temporarily in memory, and then makes its grand exit through the output unit. It's just a perfect, closed-loop system. The process is delightfully simple when you break it down into 3 steps. Try to animate this in your mind. Step 1, input. Raw, unprocessed data, like you typing on a keyboard, flows into the system. Step 2, process. The system grabs that raw data, churns it, calculates it, and completely transforms it. And then, step 3, output. That newly processed data is pushed out as actual meaningful information. Input, process, output. It's literally the heartbeat of all computing. To really picture this, think about the gatekeepers, our input and output devices. Our hardware is basically the ultimate translator between our human world and the machine's binary world. The input unit takes human data, like a click of a mouse or a scan from a magnetic ink character reader, and translates it into binary code, the zeros and ones. The output unit, it just flips the script. It takes those electronic binary signals and converts them right back into a human-readable form. That's your monitor rendering a vivid image or your printer spitting out a physical page. Moving right along to Section 2, inside the computer's brain. Let's zoom right into the absolute core of our block diagram, the processing center. We're talking, of course, about the CPU, the central processing unit. Now, we throw that term around all the time, but we really need to recognize its absolute authority here. It is the literal brain of the operation. It doesn't just do math. It guides, directs, controls, and basically governs the performance of the entire system. Every single component we're talking about today, they all report to the CPU. Now, what's really interesting about this slide is how perfectly it visualizes the math of computer memory. At the very bottom, everything is just a bit, a simple 0 or a 1. But group 4 bits together, you've got a nibble. Group 8, that's a byte. And from there, it just scales exponentially. 1,024 bytes make a kilobyte, then you jump to megabytes and gigabytes. To put that into perspective, it helps you realize how a massive high-def video file is really just trillions of tiny 0 and 1 switches rapidly flipping on and off. Mind-blowing, right? So how do all those bits actually get around? Well, visualize a bustling city with a massive network of high-speed highways. In a computer, these invisible highways are called physical connections, or buses, and there are 3 specific dedicated lanes. You have the data bus, which physically transports the data itself. Then there's the address bus, which carries the exact memory location, the address of where that data needs to go. Finally, the control bus. Think of this as the traffic lights. It sends out control signals to keep the whole system running smoothly without crashing. All right, Section 3, the memory hierarchy. Let's explore where all this data actually lives while it's taking this journey. Memory in a computer is a constant balancing act, and you can clearly see this trade-off in this side-by-side showdown. On one hand, you have primary memory. It's directly accessible by the CPU, so it's incredibly fast. But it's temporary, it's smaller, and it's expensive. On the other hand, you have secondary memory. Think of your SSD or your hard disk. This is your permanent, non-volatile storage. It remembers everything, even when the power is completely cut. It's way larger and cheaper. But the catch? It is significantly slower. And if we zoom in even closer on that speedy primary memory, specifically RAM, we see another important split: SRAM versus DRAM. Static RAM is lightning fast, but it eats up more power and costs a pretty penny, making it perfect for tiny critical things like cache memory. Dynamic RAM, though, is cheaper and uses less power. It's a bit slower, sure, but that makes it the absolute ideal choice for the bulk of your computer's main operating memory. Oh, and we absolutely cannot forget ROM, read-only memory. Unlike RAM, ROM doesn't just forget everything the second you pull the plug. It's non-volatile. Its most crucial job? Holding the startup instructions, the booting program that literally wakes your computer up. And what's really cool is there are several physical ways to write to these chips. You've got programmable ROMs, chips that literally require ultraviolet light to be erased, all the way to modern electrically erasable ones. Let's move to the next part and see how this builds into one of the cleverest architectural designs in modern computing, cache memory. So imagine you have a super fast CPU on one side and slower primary memory on the other. If that CPU always had to wait for the RAM, the whole system would bottleneck. So engineers brilliantly placed a tiny, blazing fast block of cache memory right in the middle to act as a high-speed middleman. Here's how that animation plays out in real time. Before the CPU ever reaches all the way out to the slower main memory, it rapidly bounces a request to the cache first. It's basically asking, hey, do you already have this data? And because the cache holds the most frequently used instructions, it's usually a hit. This simple, incredibly fast check saves precious fractions of a second, millions of times over. It dramatically speeds up your entire machine. Which brings us to section 4, making it run with software. Because let's face it, all this incredible hardware is completely, utterly useless without the invisible rules that govern it. Software essentially splits into two distinct worlds. First up, system software. This is the foundational layer. Your operating system, like Windows or Linux, it acts as the ultimate interface, allowing you to actually talk to the hardware we were just geeking out about. Then you have application software. These are the tools you actually use to get stuff done on a daily basis. That could be something generic like LibreOffice or a highly specific custom tool like Photoshop. But tucked away inside that system software are some serious unsung heroes keeping everything afloat. We're talking system utilities, like your disk cleanup or antivirus, that are constantly working in the background to ensure smooth functioning. And then there are device drivers. Remember our physical output devices like a printer? A device driver is a very specific piece of software that acts as an interface. It literally teaches the operating system exactly how to talk to and control that external piece of hardware. So how is all this software actually made? Well, visualize a 3-step translation. Step 1, it starts as source code. This is human-readable logic typed out by a programmer in a high-level language like Python or C++. But remember, the computer's hardware only speaks binary. So step 2, it goes through a language processor, like a compiler or an interpreter. This processor digests that human code and translates it, which leads to step 3, object code. This is the pure machine-readable binary that the CPU can finally actually execute. Once the software is built, there are basically two main philosophies on how it gets distributed to the world. On one hand, you have proprietary software, like Microsoft Windows. For this, you purchase a license, and the original source code is strictly hidden and owned by the vendor. On the other hand, you have free and open source software, or FOSS. Think Ubuntu or Mozilla Firefox. With FOSS, the source code is public, which allows anyone to freely use, modify, and collaboratively improve the software. So the crucial point we need to take away here is this entire complex architecture didn't just appear overnight. It rapidly evolved across 5 distinct historic generations. We started out with massive, heat-producing vacuum tubes. Then we moved to smaller transistors. From there, we scaled up to large-scale integration and then very large-scale integration, which finally gave us the microchips we know today. And now, we are firmly in the 5th generation, where artificial intelligence is beginning to dynamically alter how processing itself occurs. We have taken a massive journey today, from the simple IPO cycle of data to the intricate, lightning-fast dance between the CPU and cache memory, right up to the software that brings the whole system to life. But as we step back and look at this incredible leap, from simple glass vacuum tubes to modern neural networks and AI, it leaves us with one really provocative thought. What unimaginable components and architectures are going to build the 6th generation of computing? Thank you so much for exploring the blueprint of computing with me today.